our 451 project. We measured the ride height of the GFR car. It has an LCD cutout and some proximity sensors on the bottom with a microcontroller that we will go into more detail later. The reason why we made this is to measuring the ride height of the car is very good for active suspension, which is a senior project for next year of one of our GFR members. He will try and raise and lower the car in different situations, which is nice for different events that we have to go through. It's also good for aero. When all of the aero elements try and provide as much downforce as possible, and when you turn, you want to not scrape the ground and damage those instruments.
Here's the board that we used to demo our project on. This is a representation of what the car might be implemented as. There's a sensor at each corner, and then you have an LCD reading out in millimeters what each corner is reading. And then as a way to demo it, you were able to lift up front, back, sides, and then any other angle in between that the car might experience during a racing event.
In this image, you can see GFR's 2017 vehicle that we tried to implement our sensors onto. This started with mounting the sensors towards the driver, as well as facing a LCD display towards the driver. We also mounted the 4 proximity sensors on 4 corners of the vehicle, 2 on the front wing, left and right, and 2 on the side wings, left and right as well. This will later be used to calculate the pitch and roll angles. The wiring we used was unshielded, which caused some noise. So instead, we used a board to demonstrate the functionality of the project to the TAs and the class.
Here's the circuit for our project. In the middle, you can see the Arduino for where we did all of our controls. On each corner, we have a proximity sensor. These proximity sensors work by shooting an IR laser, and then it counts the time that it takes for that IR laser to reflect and return back to the sensor. On the breadboard here, we have a multiplexer. The multiplexer allows all 4 of the proximity sensors to run together. The sensors are all I2C devices, which is a certain communication protocol. And because of this protocol, we are able to run all 4 of these sensors as well as the I2C LCD screen using only 2 output pins on the Arduino. Moving on from there, we have the SD card reader, which the Arduino writes to the SD card using 4 digital pins. The data that we record off of the SD card can then be used later on for post-processing and looking at the outputs.
For the calibration portion of this project, we utilized MATLAB's curve fitting toolbox, which we started by taking several data points using a measurement device and our sensor and seeing at different heights what count values came from the sensor. At that point, we then inputted that data into MATLAB, and as seen in the image, we fit a second-order exponential function to our data and then used the equation listed in the image to then convert the count variable to a measurement in millimeters.
So after collecting our data with the SD card, we load it into the computer and convert it to a CSV file, which we use in MATLAB for some data analysis. In the code here, as you can see, I've read in the data and I separated all of the data into the different sensor columns. And from there, I basically calculate the roll, pitch, and ride height for the car. We also calculate the average vertical velocity and then plot them on the subplots shown here. We have the average ride height and then the ride height for each of the sensors, which is on each wheel. We have the average velocity, and then we have the average roll and average pitch, as well as the front roll, back roll, left pitch, and right pitch for the car. These can be very useful for determining how a car is behaving during competition. and it'll tell us how close we're getting to the ground and how much the car is tilting.
This is the Arduino code that we use for our project. Starting up at the top, you include all the libraries necessary for running your different components. We have the different SD card libraries, the I2C library, the library for the proximity sensor, as well as the library to run the LCD screen. Next up, we define the address, the I2C address for both the multiplexer and the LCD screen. And we defined a class for our sensor data. After that, we defined for the multiplexer which port each sensor will be outputting to. Next up is the different variables used later on in the code. Next up, the multiplexer will run through all the ports and it will initialize all the different ports for the different sensors that are connected. And inside the setup portion, the multiplexer will read through all the ports and it will determine if the sensor is currently connected or not, and it will throw a flag if the sensor does not actually register with the multiplexer. Inside the loop is when we get to do all the calibration and printing stuff. So we have at the top of the loop, it goes through all the sensors and it uses the print commands for the LCD to use the calibration data, the calibration equation that we found, to output the sensor output in millimeters instead of the arbitrary count value. And then after the 4 LCD print screens, we get into the SD card writing portion. So at the beginning of each loop, the SD card opens up the CSV file. It prints out exactly what we want in millimeters in CSV format, and then it closes at the end of the loop. And at the beginning, it will reopen, write, and then close continually.